Hello all, we are Filippo Furlan and Gianmarco Colorio from EnginSoft, and we would like to welcome you to this MapleSim webinar. I am Filippo and I'll describe you today's case from an overall point of view. Gianmarco then will show you a live example done with MapleSim. Today we are going to talk about building multi-physical controlled systems in MapleSim. We will start by examining a complex industrial automation application, and then we will show in MapleSim the construction of a subsystem, a DC motor PID controller feedback loop. During the example, we would like you to pay particular attention to how easy it is to connect elements coming from different engineering domains, in this case electrical and mechanical. Another important point to focus on are the conclusions, because the simulation results will be used to draw conclusions on how system behavior changes according to how PID gains parameter changes. And it is very important because MapleSim enables the engineer to have this information at the beginning of the design phase of, let's say, a new machine. And this can be extremely valuable in a real-world industry application. Also considering that very often this information, this understanding comes later on in the engineering cycle. So it is much more efficient to have this knowledge as soon as possible. For today's webinar, we are going to use MapleSim. It is an advanced multi-domain system-level modeling and simulation tool, and it applies modern techniques to reduce model development time and provide insight into system behavior. It is built on Maple, that is a numeric and symbolic computation engine that works as a core for MapleSim. And we will see in today's examples that using Maple to post-process MapleSim simulation results allows you to perform in-depth analysis and post-processing. And these softwares support the Modelica engine, that is standard for modeling. And MapleNet and MapleSim Server give cloud and web support to Maple and MapleSim developed applications. Today's example comes from the Stuart Platform, also known as Hexapod. It is a robot with 6 prismatic actuators that are attached in pairs to 3 positions on the platform base plate. And this design allows the platform to move a device with 6 degrees of freedom. So it is very flexible, very useful to place devices and tools on top of the platform and allow them to rotate and move freely in the space. At the core of the Hexapod system, as we were saying a few seconds ago, we find the 3 pairs of actuators, so 6 actuators, and each of them receives inputs corresponding to the desired motion of the device on the platform. You can see here the input as a trajectory given with X, Y, and Z motion passed on to the actuators and then the resulting platform. Here we can see the detail of one of the actuator subsystems, and it is squared in red. At the very core of the feedback loop there is the PID controller. The PID controller is widely used in pretty much all industrial automation applications because it allows a system in a feedback loop to chase after a desired set point, reducing the error after each iteration of the feedback loop. The main problem of PID controller-based design is the tuning of the PID parameters, the PID gains, because small changes in these values can lead to very different system behaviors, and you need to have a procedure to tune as much as possible these parameters in order to have a system that behaves as you expect. This is the problem that we are going to analyze today. we are going to explore two different strategies for tuning the PID gain parameters of the PID controller. And we will apply these strategies to a system that represents a simplified actuator of the hexapod, that is a DC motor and a PID controller. Gianmarco will now show you the example.
Hi everybody, this is Gianmarco, and I'm going to show you the example that we're gonna show today. So in order to perform the PID tuning, we choose a reduced select example. So a very simple system made with a DC motor connected to a beam without inertia, and at the end of the beam we have a mass. And so aim of the PID control is to provide a signal to the DC motor in order to keep this beam in the horizontal position, starting from a position which is a bit below the horizontal, so precisely it is a minus 0.1 radian below the horizontal position. So the starting point is a bit below, and the system is going to provide, and the PID controller is going to provide the right signal to the DC motor in order to stabilize our beam in the horizontal position. So we can now pass to MapleSim. So here is the starting point. So as I told you before, we have a DC motor, and then we have an arm, and then we have a PID control. So let's check how this model is made within a MapleSim. So the DC motor is made with a resistance, an inductor, a capacitor, a ground signal, the signal voltage generator, and also an EMF, which is a component needed to translate the electrical power into mechanical power. So this is the arm instead. The arm is formed by a reference frame, a revolute joint, a beam, a mass on the top of it, and an angular sensor, which is a sensor which is going to read the angle assumed by our beam and pass to the control system. So yeah, let's connect this component together. So in order to connect these two components is very simple. So we can click on the exit port of the DC motor and then connect it to the inner port of the arm system, and then we can connect the PID control to the DC motor. Now we can connect the outer port of the arm with the we can connect the port of the arm to our first of all we have to attach on this system also a feedback node. Okay, and then we also have to connect a custom component. So now we can connect the custom component to the feedback node and the feedback node to the PID control, and then we can close the loop connecting the outer part of the arm with the feedback node. The custom component is a component that is needed to set the angle value that we want to stabilize the system to. So in this example is 0 because we want to keep the arm horizontal, and the feedback node is just calculating the difference between the track of the signal, so the difference between the angle actually assumed by the arm and the angle that we want to obtain at the end of the simulation. So okay, now we can create a subsystem of these two systems, so the DC motor and the arm, by just selecting both of them and then going on edit and then clicking on create subsystem. We gave to this subsystem a name, DC motor arm subsystem. Subsystem, okay. We click on OK, Then we have the subsystem that is going to embed both the ARM and the DC motor, so we can easily check if everything is fine working. So yeah. Okay, so as you can see, let me just okay. Let me just reopen the model because we have some visualization issues. Just a second. So the only thing that is missing on this system is a sensor which is going to display the angle assumed by the beam. So what we're gonna do now is to tune the PID control gains in order to keep the horizontal direction. So what we want to do is to set up the control gain parameters. So in this case, we add the 3 parameters just by clicking here, which is the parameter view. We click on parameter view, and then we have the key PID, we have a TE PID, and we have a TD PID, which is the proportional constant, the integration time constant, the integrative time constant, and the derivative time constant. And we set a value of 100, 0.5, and 0.1 respectively. So as I told you before, we added a probe which is going to display the angle assumed by our beam at the output. In order to tune in order to tune the control gain parameter, we can follow 2 ways. And so the first of them is the parameter sweep. So in order to use this way, we can click on Add Apps or Template, double click on parameter sweep, and then we can click on load subsystem, and we can click on load system. Let me just maximize this window. So once we have clicked on it, we can click on this arrow and see if it's loaded correctly. So yeah, we have all the components that we need. We can now go to select the first parameter that we want to involve in our parameter sweep analysis. So we click on key PID, and we want to make it vary from 50 to 150, calculating 5 points in between. Then we can choose the TE PID, and we want to make it vary from 0.25 to 0.75. And now we can click on 5. Okay, and then finally, the last parameter that we're going to involve in our analysis is the TD PID, and we want to make it vary from 0.05 to 0.15, always with the 5 points in between. Okay, now we can click on Run Parameter Sweep. We have to choose the output that we want to parameterize, and we want to see the effect of our 3 parameters on the arm angle value. So we click on time series, and then we click on Run Parameter Sweep. Okay, as you can see here, we have 125 curves because we've run 125 simulation, which are basically the combination of all the possible value of the parameter that we set it in the parameter section. So as you can see, some combination of the parameter can make our system unstable. So as you can see, our beam is going to wave a lot around the equilibrium point, and there are other solutions that are going to stabilize the system in a quicker, and also reducing the amplitude of the overshoots of the system. So let's check. We can by checking this checkbox, by ticking these checkboxes, we can see the middle value of them. So for example, this was the initial set of value that we set it, and as you can see, is already a good value because is already a good combination of gains because the stabilization time is very low, and also the amplitude of our overshoot is not so big. But we can investigate the effect of each parameter by just removing the tick on the parameter that we want to analyze. For example, this will be the effect of the key PID constant, so the proportional constant. This would be the effect of the integrative time constant, and this would be the effect of the derivative time constant. So let's keep this setting as the best one. So we just keep the one that we set it at the beginning. So 100 for the key PID, the TI PID, we TI PID, sorry, we leave 0.5, and for the TD PID parameter, we leave 0.1. So we can now close this window. And now we can go for the second way of tune our control. So in order to do that, we have to first of all linearize our DC motor arm subsystem. So we go on linearization, and then we load the DC motor arm subsystem, and then we click on load selected subsystem. Okay, as we did before, we check if it's loaded correctly. Yes, it is. So now we calculate the linearized equation around the initial condition. So we just leave a tick initial condition configuration, and then we can press on linearize. We are doing that in order to use the PID tuning template embedded inside MapleSim, because it needs a linearized equation to perform the PID tuning. So if we now click on the graph, we can see that we have to give a name to our linearized subsystem. So in this case, we're gonna call it DC motor arm linearized. And then we click on create. Now, as you can see, on the left-hand side of our screen, we have a new component which is called DC motor arm linearized, and we can select it. In order to perform the PID tuning using the dedicated template. As you can see, both from the app side and from the template side, there are many tools that we can use, but today we're just focusing on it. But there are tools to do pretty much everything that we need in the design control process. So we can now double click on PID tuning. We select and we let me just delete this one. Yeah, we double click on PID tuning, and then we are inside the environment that allows us to perform the PID tuning. So we now choose the linearized model, and is DC motor arm subsystem linearized. That is the model that we just created. Okay, now we select the method that we want to use to tune our system. So we're going to select the Ziegler-Nichols frequency domain, and then we can click on the design controller. As you can see, the calculation time is very quick, is very low. So as you can see, MapleSim provided us free values for the PID controls parameter. So we can now click on export to MapleSim in order to use these controls. So I click on export to MapleSim. Okay, and as you can see again on the left hand side of our screen, we have a new component. Now we can recreate the same workflow just by copying and pasting the same system, so we don't want to connect this system together, so we click on no, and then we put it in this position. Okay, now the only thing that we have to do is to delete this control and paste on our screen the control that we just used. And as you can see, it's very simple to create a copy of the system. And if we click on the second PID control, we have the value tuned by MapleSim. So now, in order to, I'd like to show you both the system running together. So in order to do that, we can just double click on the second system, so, DC motor arm subsystem, sorry, and go on the inside the arm and change and give a bit of an offset to this component. So let's say half a meter in the horizontal direction. Okay. Browse back to the home section and let's see if we have two systems now. Yes, now we have two systems. So, okay, as you can see, we have now two systems, and yeah, we have to also to give it to the assistance to this beam first. Sorry, inclination. So we go back here and we give to this. Okay, we check. I'm just checking if everything is correct. Sorry. Okay, so now I can update the view. So it's gonna. Okay, as you can see now we have two systems. The first one is the old system and the second one is the new system created by copying the first one, and they both incline below the horizontal of 0.1 radians. So now what we want to do is to see which system is going to perform the best. So we can just click on run simulation. Okay, and then we can see these two systems running together. So as I told you before, the one this system is the old system, so the one that we tune using the parameter sweep, and the second system is the one that we use tuning the PID control with the tool embedded inside the PID tuning template. Sorry. So if we press on play, we can see that these two systems have different performances, especially the one tuned with the dedicated template goes to the horizontal position much quicker. Just to see better result, we can just zoom. So we end the simulation in 3 seconds. So the whole video will be involving just the stabilization phase. So we can click on play again. And then we can see again these our two beams aligning on the horizontal position. So in terms of graph, we can then check numerically how these two systems are working. So we go on the graphs, and then we we click on the last results. So as you can see, this is the angle over the time of the first system, so the one that we tuned with the parameter sweep, and the second one is the one that we tuned using the PID tool embedded inside MapleSim. So they have different performances in terms of both overshoots and also stabilization time. I would say that I would prefer personally the second system, because as you can see, the overshoots are lower, and also the stabilization time is lower. So, but this is a decision that have to be demanded to the designer for the control. So, for what I would like to show you today is also in today's case study, I've demonstrated the two approaches that we can use in MapleSim to perform the PID tuning of a control system. If you have any question, I'm giving you a few minutes to write them in the dialog box. So please don't hesitate to ask any question. I'm seeing that a few people are asking if the webinar. If the webinar video is available, yes, of course, we're gonna make it available to you guys, so you can download it and you can watch it whenever you like it to. So I'm gonna show you the slide that contains the contact in order to contact us if you want to have further information on MapleSim. So this is our contact, so EnginSoft SPA. Part of our competence center, and under this link will be available shortly the video of the webinar of today. From my side, if there are any other questions, is all. I thank you for joining our webinar today, and hope to get in contact with you soon. Bye.